476 millivolt in one and 500 millivolt in the other.
You said that this issue got resolved using some other technology node?
Yes, sir, that got resolved, but only when I was adding the cascode on the left hand side. Without the cascode, it's not getting resolved.
Did you check the gain at that point? When you go to that point, what is the gain?
Yes, sir, I checked. I'll show you.
What is go back? What did you set up? Just show me the value again. Okay. How much is the input signal magnitude? What is the input signal magnitude? 0.1 millivolt. Here, what are you getting? 830 to 870. That means just around 40 millivolt. So 400 gain you are getting. $400 is not bad, but you can improve. What is the AC analysis plot? 400 means the gain of the individual stages is poor, or basically the cascode stage you need to improve the gain, GM you need to improve. So 46 dB, that means something similar to, what you are getting. So which will be for around 400 gain. And the cutoff frequency right now is go to that 3 dB point. So 3 dB point is so it is much higher than 10 mega. So you have enough. What is the phase margin? Phase margin is so go to 0 dB point. Phase margin anyway you can improve, but right now you have enough bandwidth. So bandwidth you can reduce and you can increase the gain. So there's a lot of room for increasing the gain. The phase is also not good. So phase is only 10 degree. So starting from, so where is the phase starting from? If you have taken from positive input, right? So phase is starting from 180 degrees. So you have taken from negative input. And then the next phase shift you are getting is almost close to 10 degrees. So phase margin is not very good. So you may have to put a cap over there, but gain magnitude you can definitely increase. So what is the size of the input device? You can increase it further, make it maybe 40. Output side, what is, let's see the output stage dimension. You can reduce the current, make the current 5 micro. Output side, showing the dimension. Go down. So you may have to increase the L. So make both of these also larger. So W and L both you can increase. So W you can make it 40 micro and length you make it 90. 90 nano, not micro. You have you will have to change the mirroring. So just look at the mirroring because you have the mirroring ratio has to be maintained. So this one you have increased W and L both. Downward side you have increased W and L both. Close this, and the middle side the ratio is same. So fine. This to this ratio anyway you have not changed, and the current should be remaining similar, so this should be fine. What is the ratio between M3 and 12? That ratio I thought that is same, right? Whatever I provided. Check M12. Okay, close this. Check the plot. Do the AC plot again. So there are two multiple poles coming. You have to change the DC value. Change the DC value so that again it is you have to find out the new point. There is another way of doing this rather than changing the DC sweep. Where you can also connect a large inductor in the feedback unity gain. The inductor value omega L at DC will be 0. So it will all for DC it will act like short circuit, but for higher frequency it will act as open circuit. So for that we need to put a L which is very high. Theoretically it will work just for the analysis. There is slightly improved, so it is now coming 53 dB. So this is similar to what you have obtained earlier, right? So earlier also in that two-stage op-amp you obtain something like 56 dB. Here you are also getting something similar. You want to improve further, again, output stage you can modify, you can increase the length of the output stage. So let us try to do that. Output stage you can maybe try to increase the length further. But W and L both has to be increased, so make it 180. Input device also you can increase. No, input device length does not matter. You don't need to increase the length of the input device, only the W. Which device is this? What are you doing? I sold only the input device. Which other device have you modified? M9, M10 will not be modified because that will affect the ratio of the second step. Current you can again you have to change that. You have to get the DC point. Just drop.
Yes, it has dropped.
So there must be some problem in the sizing somewhere. Check the sizing once again.
Yes, sir. This is 45 nano micro. This is 45 nano 80 micro. 41 80, 20 50. 80, 40, 185, 40, 180. This is
Or the DC
20.
point is not accurately chosen. Did you check what is the DC point? Check the output DC
Yes, sir.
point.
Yes, I will show the. I'll just sweep once.
You choose a shorter range so that it is doing more accurately. Just close to that value only.
Yes, sir.
Here, no, this is not enough. If you are having very less points, so what you do is just select the intermediate, the smaller range, keep between 370 millivolt and 380 millivolt.
Yes, sir. See.
Increment, you make it even smaller. 0.1 milli.
Yes.
0.01 is also fine. Just do it more accurately.
Yes, sir. So 0.1 will be more fun. Still very sharp. P74, 78 me. Yes, sir. Now it is giving a good gain. Like I'm getting 110 dB.
Yes. So 110 dB is good.
The
Look at
bandwidth
the
has degraded.
phase margin. You check. Bandwidth will definitely, once you increase the gain, bandwidth will go down. That is obvious.
107. Phase margin is bad, sir. Around 12 degree phase margin.
So that is okay. You'll have to put a cap so that you can compensate. So you put some cap, maybe 50 femtofarad. Put a cap of 50 femtofarad.
I've put, sir. It's here. It's now at 22 degrees phase margin. I think I'll need to increase the cap further.
Sorry, once again.
Sir, it's at 22 degree now, the phase margin. I think I'll need to increase the cap further, like around 100 femtofarad, I guess, or 200 femtofarad. Degree. Sir, now I'm getting almost 41 degree phase margin.
Look at the 3 dB point, and it is going very down because the gain has been increased.
Hello. So
Yes.
it has gone quite low, sir. It is around 400 hertz now.
Yes, that is expected because your gain is so high. So it is expected that the uh, bandwidth will be poor.
Yes.
So here, this is almost like even go to that DC close to origin, almost 110 dB. Not origin. Origin when it's close to DC, zero value, and then the zero frequency.
Oh, yes, sir. Started from 100 hertz, so I need to go to sweep. This is near the origin.
Yeah. So 110 dB is almost like 30K. So that gain is pretty high. Not 30K. It is coming 300K. 100 dB and 110 dB is 300K. So I think the earlier
Second.
values also you might have got very good gain, but because you did not check the I think the resolution of the DC analysis should have been done properly so that you got uh, appropriate DC. So for earlier values also, if you had done the analysis properly with higher resolution in the DC analysis, you will get the exact DC point so that the gain was higher. So this much high gain we may not be requiring unless the application demands that kind of gain. So here, if you look at, say, this is 13 10 power of 4 gain, which is pretty high. Generally, for this kind of even front-end amplifiers that we need, maybe at max we will need is 80 dB gain to 90 dB gain. So here, if you want to improve the bandwidth, there is a opportunity there. You can sacrifice the gain and improve the bandwidth a little bit. But for the time being, you can just try to confirm. You can do a small signal analysis. Maybe you can do a transient analysis also just to confirm So with this DC condition, maybe you can apply a very small voltage at the input, maybe 0.01 millivolt or something, and then see what is the effect. 1 microvolt. You can apply 1 microvolt.
1 microvolt. Sir, 1 microvolt, it results in a peak-to-peak voltage of 200 millivolt approximately. So the gain will be, sir, around 10 to the power 5.
So peak to peak amplitude of input is how much?
Sir, 2 millivolts, sir, peak to peak. 2 microvolt. 2 microvolt.
Yeah.
And this is
so then it is
200.
100. So this is 10 to the power of
Around
5, around 10 to the
10
power
to
of
the power
5 gain.
5.
Because you have taken a higher frequency, if you go lower the frequency, it will further higher. So you can lower the frequency.
So I'll put it 100 hertz. I think it is getting clipped.
So you're clipping, that means you will need to gain is more than that.
Yes, sir.
So then you have gain is more than the output range. So gain
Yes,
is
sir.
so high that the output is clipping. Output range, it is going beyond it. So you need to reduce it further. Make it 1 millivolt peak to peak. Oh, sorry, 1 microvolt peak to peak.
So it was 1 microvolt. I'm making it 0.1 microvolt. Now so it's around around 3 into 10 to the power 5.
Yeah, so this is confirming the AC analysis. Whatever we get from the AC analysis, the same thing is coming here.
Yes, sir. And sir, what I wanted to ask is that why is it happening that I have to put the common mode voltages at different levels?
That is some anomaly with the model. So there is some issue. I think the way they have modeled the channel in modulation may be having some problem. But this is not correct. Means in actual scenario, it will be very close.
Yes, sir.
So this is showing that the systematic offset in the circuit is so big. But generally, that is not the case. Systematic offset will be fraction of millivolt. We have seen that earlier also. Here, somehow it is giving that kind of difference. Generally, this should not be the case. Here, there is, in the two parts, there is good amount of asymmetry, but still the gain, and the other thing is the gain of the first stage is also limited. So because of that limited gain of the first stage, it's possible that it is basically because the two paths are having asymmetry, and even the gain of the second stage on the left hand side is also less. Most of the gain is coming from the output stage.
Yes,
So because most of the gain is coming from the output stage, a difference in the input in the first stage, the DC level input difference, it is not translating so much to difference in small signal currents. The DC point of view, maybe the currents are the DC currents are, so look at the DC currents of M9 and M10 in this condition. What is happening?
Yes, sir.
Because here what we need is that the output should be close to the midpoint. And for that, whatever input difference you need to have to get that, we need to apply.
Sir, in M9, we are getting almost 2.7 0.27 microamperes.
M9 is
This thing.
wait a minute. M9, yeah, M9 is 0.27 microamperes.
Microamperes.
Which one is the M9?
1 minute.
Show me
sir.
that.
This one is M9, sir.
What is the current in M3?
It's so.
M9 current is very low because the DC current difference is. So basically
Sir.
here most. So this is same 5 microampere.
Yes,
but
sir.
M9 is taking very less current. That means most of the gain is coming from the M10 side. M9 side, you're not getting much gain. So
Yes,
M9
sir.
side.
So most of the current has been taken by M10, as we can see.
Yes. So that means that the gain is mostly coming from the M10 side. M9, M1 side, M9 side, it is not having much signal. And that is not good actually, because this will also mean that you're going to get good amount of common mode gain. So here it is becoming, what you can do is just try to apply the signal you have applied to the gate of M2 or M1, M2 or M1.
Sir, I have applied at the gate of both, like V in 1, V in 2.
What you do is just apply it at the gate of M1 only and see what is the situation.
Yes, sir. So I'll put the M2 at DC bias, right?
Yes. This circuit, it does not give this kind of behavior. There is some problem with this PTM model why we are getting this kind of asymmetry, because in cadence, etc., this circuit behavior is not like this.
So we are getting again.
Similar.
Yes, so there is a gain of around the same thing which we applied first. What we got first.
Okay. So then, of course, you do have similar differential, like differential property, differential characteristics is coming, but bias current is a big skew, and that skew is so there is an input output characteristics. That input output characteristics is the DC characteristics. If I look at it, there you are getting the high gain region at a certain point where the difference is big in the DC, and the current difference is also big. Now, what is the DC current in M14? M14 current also must be very less, I guess. So just check what is the M14 current.
Yes, sir.
14, 14.
So it's 1.6 micro.
And what is the M? What is this? My eyes have become weaker. What is this numbers? M14 and what is M6?
M6. M6 is. Sir, same, sir. 1.6 micro.
So M14 and M6 currents are same, but M9 and M10 currents are very different. Is the mirroring ratio very different? M9, M10, M9. Just check the mirroring ratio. M9, M14, M10, M6.
5, 1, 10, 5, 10, 45, 10. So all the same, sir. The W by L ratio is all same.
Okay, and the lower side. So this is the M9, the M14, M6 currents are also similar.
Yes.
And other result, M5, M7 current should also be similar. You can just check M7, M5. Almost, of course, it will be similar only. Same values.
Yes, sir. They are the same value.
Okay, close this. Let's slide this window towards some corner. So these two currents are same. These two currents are same, and despite that, we are getting large input difference. DC point of view, there is a significant difference. And mm,
Sir, although sir M14 and M9 both are in saturation, but in any case, the current being mirrored is largely different.
little strange, means some of these things are model, I think, inaccuracy problems. So, of course, what we have in this case, what we have is that the net difference in the net gain of the first stage is low. Only thing is it is providing a transconductance operation. So it is converting the input voltage signal into differential current signal and then sending it out. So what you can do is, let us see, just to try to analyze it a little bit further. What is the small signal current being produced? So you can look at the drain current of M1 and drain current of M14. Likewise, you can look at the drain current of M2 and drain current of M6. So how much small signal current is traveling from M1 to M14 and M2 to M6? Are they similar or are they very different? Let us look at that.
Sir, you said drain current of M14.
Yes. And source, you can say the PMOS, you can look at the source also. Peak to peak value.
Yes, sir. Around 62 63 picoamperes, where I have applied around 100 picoamperes.
What do you mean 100 picoamperes?
Oh, sorry, no, I mean volts, 100 0.1 microvolts.
You look at the small signal peak to peak current of M14 and M1. I need both
Yes,
of
sir.
them.
Yes, sir. M14 and M1. Sir, M1 is 12 picoamps, whereas M14 is 63 picoamps, peak to peak.
M1 is 12 picoamp and M14 is 63 picoamp.
63 picoamps.
And what about M6?
6.
So here we are trying to see the peak to peak current.
Sir, M6 is 51 picoamps.
So again, peak to peak currents in M14 and M6 are similar.
Yes,
so the magnitude of peak to peak AC signal in M14 and M5 are similar, but the DC current is also similar. But the M9, M10, here we are seeing that the DC currents are very different. And despite that, the AC signal is coming similar. This is a little bit contradictory. So there is some. So look at the small signal AC current in M9 and M10. They will
Sir,
also be
it's
having
12 picoamps in M9 and M10 both.
both M9 and M10. You are getting 12 picoamps.
Yes, sir.
So but the DC current is different, very different, right?
Yes. Yes, sir.
So the DC currents are different. The gate DC currents, the peak to peak signal is same in both M9
Yes, sir.
and
Same.
M10.
Yes, sir. M9 is same.
So M9, M10, same AC current and the same AC current in M14, M5 also, but the DC current in M9, M10 being very different. The GM will depend on ID upon viewer drive. So what is the gate voltage of M9 and M10?
Yes, sir. Gate voltage.
Dimensions are same, right? M9 and M10 dimensions are same.
Yes, sir. To do
Gate voltage of M9 and M10?
Yes, I have to do the DC analysis.
No, I mean, yeah, DC operating point analysis.
Yes, sir.
If you just plot it, you will get it. So the DC voltage will be the average point, right? So whatever peak to peak signal you are getting, the average.
So it's 974 millivolts at gates of both M9 at gates of M9 and at gate of M10 we have 852 millivolts.
So overdrive voltage is different. So overdrive
Yes, sir.
voltage of M10 is less.
Yes, sir.
Sorry, higher. Because VSG is higher. So ID upon 2ID upon V overdrive. For the same ID, the overdrive voltage of M10 is coming smaller, higher. As a result, the GM is smaller. So effectively, what we are seeing is GM of M10 is smaller than GM of M9.
Sir, but the IDs are also different, right? As we saw, the ID of
ID
M9 is
also,
different.
Acha, ID is also different. ID is also vastly different. So most of the ID is flowing through M10. So 2ID, ID is much bigger, and then V overdrive.
So ID is also higher, V overdrive is also higher. So maybe that the GM is getting compensated on both sides. Although not by that amount, but still it will be somewhat compensated, right?
there is some problem. Another thing is, can you just change the, so this should not have much effect, but the body terminal of both M1 and M2, you connect it to ground. All the NMOS body terminal, you connect to ground. It will not be connected to source.
Yes, sir. The remaining, yes, these are not connected. So it's not giving much change. I've connected all the points to the ground, the body terminals to the ground of all NMOSes.
There is some problem with the model somehow, means because the small signal currents are coming similar. DC current in the two outputs, like the left hand side, right hand side, second stage is also similar, but somehow the DC point of view there is difference, and as a result, the DC currents are also similar. So M6 current, M14 current is also same. DC current is same, right? M6 and M14.
Yes, sir. They are same.
So despite difference in the VSG, the DC current is same. That may be because again this site has a different kind of channel and modulation. But I think there is
Sir,
some problem in the.
So one thing which I noticed while doing the simulation was that when I'm mirroring from a 45 nanometer length MOS to a 45 nanometer length MOS, then the mirroring is not effective. But when I'm using this 180 nanometer MOS to bias the currents, then all the currents are approaching the same value, which is why I introduced this cascode in this leftmost branch so that I can bias it using this 180 nanometer MOSFET. In
No,
that case, all
that is not required, right? So here we are getting it without it.
yes.
So why are you again mentioning that?
Sir, but the currents are not coming the same, right? But in that case, the currents, DC currents were all coming the same, all coming 5
That is because the
microamps.
loading effect will be on both sides will be similar. So the circuits are symmetric, and you're getting, the channel and modulation effect on the M6 will be same as channel and modulation effect for the M4. So the circuit become very symmetric, but that is not going to kill your phase margin issue. So phase margin will be worse because you are going to introduce two similar poles. So there is no advantage of going to this topology. So in this case, at least the DC behavior should have been correct. AC behavior is coming correct. The DC point of view, we are seeing that M9 and 10 current are getting skewed. That is not expected. Generally, in this circuit, we don't expect this kind of strong skew. So here, the one of the reason is that the two sides, the M14, M5 side, the for the M14, the loading effect is very different. It is just having a direct connected M5, whereas for M5, the loading effect is very different. It is having a high impedance load. So for M6, if I see M6 at the top, it is facing only, it is facing M11, M8, and M7. So if you look at the impedance phase by M6, it is almost like RO, right? So the impedance in the drain of M6 looking downward is RO. And impedance for the M14 is 1 upon GM. DC point of view also, the M14 is facing only a single MOSFET. Of course, the VGS of this MOSFET should be decided by the current. But on the other side, it is facing three MOSFETs in it's facing three MOSFET in cascade. So 3 MOSFETs are cascaded, and then you are having a this is going to have a very different channel length modulation effect because the VDS constraint is going to be much tighter for M6. So that may be the reason in this scenario, because the output state, the channel modulation faced by M6 is very different than the side of M14, M5. As a result, it is creating a difference in the input voltage, so that for a output voltage to be midpoint, we are requiring a significant difference in the input voltage, uh, so that we are in the high gain region. But generally, I mean, we have not observed this kind of thing in your cadence tool. So the way lambda equations have been modeled, maybe that has been different over here. So for the time being, I guess if you want to make it more symmetric, then one possibility is that here, just like you are biasing the M8, M8 is biased using the mirror, M7 is taking the current from this one, and likewise this guy. So if we want to bias it some other way, that would be tough. Even if you bias M7, I think this is fine. I don't think we need to change anything. So we need.
Sir, we cannot bias M7 externally, right? Because it's already coming from the M5, or otherwise it will not work like the way we did, right?
You can bias it from another mirror also. That is also possible, but you have to make sure that your the branches, M7, whatever mirroring circuit you are using from there to M7, that ratio should be symmetric, upside ratio, downside ratio. But for the time being, I don't see any major change that can be done to improve this. So this issue, I am not very sure at this point why this big difference is coming. And the only issue that I'm seeing, only reason for this that I'm seeing is the asymmetry in the right hand side output stage and the left hand side second stage constituted by M4 and M5. The M4, M5, the loading effect that M14 is facing, M14 and M5. So the loading effect faced by M14 is very different, and loading effect faced by M6 is very different. And as a result, DC point of view, if I calculate the DC currents in M6 and M14, the DC currents are coming similar, because right now we are forcing the output to be somewhere midway. We are changing the input DC condition so that the DC currents are somewhere midway. And for producing that midway DC current, we are having to increase the V in 2, right? The DC of the V in 2 is higher, or V in 1 is higher? V in 2 is higher.
Yes, sir. V in 2 is higher.
So V in 2 is higher, and that as a result is pushing more current in M10. And but if you look at the DC currents in M6 and M14, they are same. So if we now, what is the conclusion of this? So M10 is forced to have higher current so that current of M6 and M14 are matched. Because remember that the output DC point, when it will be very close to midway, when the pull up and pull down currents are same. That means M611, M11 current is the pull up current. Whatever is the current provided by M6 and M11, if that matches very closely with M8 and M7, that of course in the real condition, when you connect them together, it has to be same. But saturation region, initially what will happen if you see in the case where you're putting V in 1 equal to V in 2, what is happening there? Because the channel length modulation effect for M6 is stronger, you are having a load of 3 transistor. As a result, VDS is going to be small. So VSD of M6 is small. As a result, the channel length modulation effect is coming strongly. And then what is happening for the same gate voltage of M9 and M10, M6 is carrying lesser current, right? So when you're applying same voltages V1, V2 at input, DC voltage is same, M9 and M10 will carry the same current, and VGS of M9 and M10 will same. And as a result, the VGS of M6 and M14 also same. But now M6 and M14, The M14 is having a larger VSD, right? Because it has only one M5. So the source to drain voltage is large for M14. Whereas for M6, the source to drain voltage is small. On the other side, M6 is having three other transistors in stack. As a result, the source to drain voltage of M6 is coming small. Despite the same VGS, the M6 is sinking. M6 is having lesser current as compared to what M7 would have. To compensate for that, the output voltage goes down so that the current in both of the branches become equated. Ultimately, it has to be same, right? M6 current has to be same as M7 current. But now, because of this condition, because of the smaller VSD, if I assume that the VDD was halfway, the VSD of M6 will be much smaller as compared to VSD of M14. Now the current in order to equate the current, we need basically the output to go further down, because if it goes down, then only the VSD of M6 and VSD of M6 will be increasing, and it will be becoming similar to the VSD of M14. That case, it will try to equate the current. That is what is happening. So that means that the channel length modulation is very significant. So here, the lambda value that you are getting is pretty large. That's what I'm expecting. So if the lambda is significant, then because of the channel length modulation, in case of V1 and V2, V1 and V2 being exactly same, M6 and M14 currents are not having similarity. They are very different because of the channel length modulation faced by M6. And then we are forced to increase V into so that now M6 current is increasing, and then the M6 current is becoming similar to the current in M14, because only then M6 and M14 current will be same, and as a result M6 and M7 current will be same, and then only it will go to midpoint. Output will go to midpoint. Is that clear to everyone? Are you able to understand the issue? So this is because of channel length modulation faced by M6 and maybe a larger channel length modulation parameter. Is this point clear? Nobody understood. Let me try to draw and explain. Anybody understood what I said? Nobody understood. Anyway, so I will try to draw and explain. But for this value, you are getting large gain. Bandwidth is poor. If we want to trade off, definitely we can sacrifice the gain and improve the bandwidth. And now using this circuit, right now we are getting almost 30K gain at DC. So if you want to reduce it a little bit, it's possible to maybe go down. So for doing that, maybe the input device, what you have, just show me the sizes. Yes, am I audible?
Yes, sir.
I don't know. Are you able to hear me?
Yes, sir.
Yes, sir.
Sir, I got disconnected, unfortunately, due to poor network.
I don't know whether other people have done anything, or they are listening or understanding, or they are just sleeping. Yes, what happened? I don't know. I think there is some connection problem, and who was sharing?
Hello.
Sun was sharing.
Yes, sir. Sir, I got disconnected because of the connection, sir. I'll
Are
share
you going to
again.
share again? Means I'm not able to see the screen.
Yes, sir. I'll share it again. Yes, sir. Visible, sir. Hello.
Yes. So
Yes, sir.
you can. Did you understand whatever description I gave regarding the mismatch?
Yes, sir. Yes, sir. I got it, sir.
Other people, anybody else understood? Or are you listening, or you are all of you are sleeping? Ayan Adhikari, can you unmute yourself? Let me try to do some survey.
Yes, sir.
So did you understand what I discussed regarding the difference in the input DC voltages?
Yes, sir.
What did you understand?
So, like due to this asymmetry in the circuit, there is a difference in this DC operating point, which we will get from the DC transfer characteristic. So, due to that, this there will be a difference in the DC level of the two input devices.
No, why there is the difference between the two input device DC?
So, because of the asymmetry in the circuit.
That I explained further, right? So what is the reason for that asymmetry? Anybody else? Amresh Kumar De?
Hello.
Yes, did you understand what I discussed?
Remotely, sir.
So what did you understand? Yeah, can you explain?
Means there is some asymmetry due to the
So the absorption capacity is very poor. Means I'm explaining certain things, and half the people, most of the people are not understanding. So I have to slow down maybe, or to use some pen paper to explain, or basically use the drawing to explain. So let me, you know, so I think at least as far as the gain concerned, he has already shown a big gain, and you have only issue is that the input required DC difference is pretty significant, and bandwidth is low. Compensation has been done to get the phase margin required. Transient value is also coming. Whatever is the AC response showing, same transient response is also coming. So these things are done. Of course, now this op-amp can be used for doing useful things. But before that, I would like to reduce the gain a little bit because we may not require such a high gain. So in order to make this op-amp useful for future, work, let us try to reduce the gain a little bit. So M1, M2 dimension just open. What is the M1, M2 dimension?
Yes, sir. So M1 is 80 micro by 45 nano.
You can make it 40 micro. And output side, let's see the devices. Output side length is 180 right now.
Yes, sir. So all of
Not
them have
bad.
180 length.
Okay, 50, 180. So you can maybe try to simulate now. You will get some reduction in the gain, not so much. Again, the DC point will change, everything will change. So the
Oh,
DC
yes,
point.
yes, yes. Yes. I have to do the DC point again.
What you can do is you put a big inductor. So let us just to use a shortcut method. Let us try to put a big inductor between the output and the negative input, so that you have a voltage follower kind of configuration. But the inductor value should be very high. You put it something like 10 to the power of 9 Henry, 1000 mega Henry, something like that. Or even more than that, means 10,000 mega Henry.
Sir, 10,000 mega Henry.
Yes. The reason for doing that is that for DC, it will become short circuited, but for any significant AC signal, it will be open circuit. So that means that in your AC analysis, it will ensure that the DC point is, or you can basically, rather than connecting it this way, you can also one. So yeah, that is also fine. So in terms of AC analysis, what it will do is it will just make it shorted. As a result, it will work like a voltage follower, so that V in 2 is, but the problem is that you have a DC point also. So DC point of view, when you are forcing it, V in 1 DC you will have to remove. So V in 1 DC you will have to disconnect and apply the AC signal at V in 2. That is a shortcut way, basically, rather than doing the AC analysis every time. This is just for simulation purpose. So this will basically force the DC condition to be as a voltage follower, so that the V in 1 DC is fixed to the V in 2 DC, and it is following very well. And the AC signal point of view, L1 will block any AC signal. So AC point of view, it will remain blocked. And the signal, when you apply any signal to V in 2, V in 1 will be something like an AC ground. So that point of view, you will not need to find the DC point all the time by sweeping. That is the only benefit that we are going to get. This is just for ideal case, and just trying to is just a trick for establishing a DC point in the open circuit case, because generally the op-amp will not be operated in open circuit, it will be always in feedback. So in the feedback case, this DC will automatically come. But for the open circuit case, when you have to do the open loop analysis, in advanced tools like Cadence, there are ways in which it can be done. There is the open loop analysis setup where you don't have to necessarily open the loop and fix the DC point, just like what we are doing here. But here that this feature is not available. So this is an alternate trick just to basically avoid that DC sweep. So
maybe some problem is occurring.
So what is the DC of, did you remove the V in 1 DC?
Yes, sir, I removed the V in 1 DC. It's purely an AC signal now.
No, you remove that signal also. There is no signal at V in 1.
Okay, sir, I'll remove all signals then. I'll just delete this. Not working.
And the AC signal is applied as the V in 2.
Yes, sir. Sir, V in 2 will have a DC offset, right?
No, you put whatever DC, so you put close to VDD by 2.
Okay, sir.
So what we are trying to do is we are trying to put it in voltage follower configuration. As far as DC is concerned, for DC omega L is 0. So it is like a voltage follower for the DC. So whatever is the output voltage, it should automatically develop. It should be equal to the negative terminal voltage. Or you can do the DC analysis also and try to find out what is the DC voltage is coming. This is just a trick. I mean, there is generally we don't use this in Cadence. In this particular tool, that feature is not there. That's why we are using it. So open loop analysis, the way you are doing right now, it is requiring a STB, it is requiring a DC point calculation. First, you are trying to find out what is the appropriate input DC level so that the output is at the midpoint, and then doing the AC analysis. But using this approach, so you're not getting actually. So the DC point of view, just look at the DC voltages at different points. What is the DC at V in 2?
Yes, sir. Just a minute. I'll simulate the DC operating point. Sir, at V2, I've put the DC voltage as 0.5 volt.
And what is coming at the gate of M1?
Yes, sir. Yes. At the gate of M1, we have something like this, around 482 millivolts. Same thing.
Okay.
Around.
Same thing means whatever you are getting earlier.
Yes, sir. At yes, sir.
Yes. So the same will be at the output also. The output you will also get similar.
Output is also same following this.
Yeah. So as we expected, the inductor is going to be shorted at DC. As a result, the DC point of view, it is acting like a voltage follower. But there is a difference between the two sides. Now, if you look at the current conditions, that will also be similar. So whatever current you are applying at earlier, whatever current we saw in M9 and M10, you will get similar. So just check the DC current in M9, M10.
Yes, sir. No, sir, it's still coming different in M9 and M10.
That's what I'm saying. Whatever you were getting earlier, the same thing will come.
Yes, sir. Means what we got in the earlier case, that value came, exactly that thing came.
The same value is coming, right?
Yes, sir.
That is expected because we have converted into voltage follower configuration. Now for AC, it is not giving any gain. That is surprising. So close this and apply here. The problem is that the AC signal, the bandwidth is very poor, and that's why we are probably not getting, because for lower, what you do is increase the inductor magnitude further.
So still higher.
Because what is happening, maybe the AC signal, because bandwidth itself is very poor. So AC point of view, we have to see. So now you do the AC analysis.
Is giving unity gain 0 dB.
It's not 0 dB. It is that green curve, which is 8 dB around.
No, sir, it's my 14 micro dB. And just see.
Okay, so here that means the AC point of view, omega L, right? So I was expecting that even for small frequencies, omega L, the impedance will be very high and it will act like open circuit, but that is not happening. And we are, so that means it is 0 dB gain. That means you are getting unity gain. Unity gain is not expected here because L will be open circuit, but that has not happened. You have a
So
C.
maybe if we change the DC bias of V into.
No, the DC bias is already whatever you have, so it is automatically coming. So that's the reason why we use L1, so that we don't have to check the DC bias condition. But this is AC point of view. I was expecting that it will act like an open circuit and it will give you the gain, but that is not happening. DC, it is coming properly, but the AC gain is gone. And that's why we had put large L so that the AC, we get it blocked, and from V into to the output, we get good gain. But that did not happen. So maybe you, let me think. Maybe put a small resistance in series with L1, maybe put some resistance, maybe 1 ohm, something like that. That should also not create much difference.
No, sir, no difference.
And LC, C is here. So can we, the DC gain, AC point of view, shorted, open circuited, but still not getting anything. Output DC, you check, output DC is coming properly. Output DC anyway we saw, so that was coming properly.
Yeah.
But AC gain is not coming. So although it is ideal L, and omega L should be very high, even for 100 hertz, omega L is very high, but that's not coming.
I've increased it already to 1 kilohertz. Still it's not.
Maybe you can just do one transient simulation, apply a sinusoid at the input V into and see, just like earlier you were doing a very small signal.
Yes, sir. I've applied a sinusoid at V into. Matrix. So it is saying that there must be some singular matrix.
It is not able to simulate, so you leave it. So this simulator having some problem. So
Sir,
you
one thing is that is this capacitor getting any problem, sir? Because this inductor is there and then this capacitor maybe, I don't know.
that should not have been the issue. So capacitor, even if you remove it, I don't
No,
think it
it's,
will resolve.
no, sir, it's not. It's still giving failure.
We leave this for the time being. In this tool, we have to stick to that same approach where you find out the DC appropriately and then apply the signal. So right now, you are getting proper, gain. So you are all
Yes, sir.
set. And the only thing is, this kind of high gain we will not be requiring. And here 300K gain was coming, which is also a little surprising. I was not expecting this kind of gain. I was expecting maybe something like of the order of 10K, means something like 30K, 40K, but it is 300K. So we have some margin. We can reduce the gain also by factor of 10x. Then also we will have good enough resolution. So how much gain to have? It depends upon many things. It depends upon the target precision. It depends upon like if you want to have a very high precision gain in the amplifier. You remember that if you make a feedback amplifier, the open loop gain plays a role, right? So ideal gain is just given by 1 upon beta in the feedback amplifier, but it is having a factor of 1 plus A naught beta divided by 1 plus A naught beta something. So that A naught beta, if this A naught beta is uh, much higher than 1, that means A naught is much higher than 1 upon beta, then you get more and more accurate result. So here A naught is much higher than 1 upon beta. A naught is, your A naught that you have is 300K. So here, even if you want to have, say, closed loop gain of, say, even 1,000, even a closed loop gain of 1,000 can be achievable here. So we will discuss that part a little later, that, how to decide the op-amps, open loop gain, etc. But before we proceed further, I will discuss some more things, maybe something regarding the output stage and the output impedance, buffering of the op-amp. So let us stop recording here. I will start recording again, and then I will discuss some theory part. Also, I will discuss some people, or majority of the people did not understand this mismatch issue. So I will explain that on, on the board as well. So let me stop the recording, otherwise it will become too big. Stop recording. Happens in the beginning, a lot of people will come with a lot of enthusiasm, but then as we start going deeper into assignments, many people are not able to follow. So I have started recording again. I'll share the screen and go to a new page and cover a few more things. So related to whatever, we have, what happened. Screen, wait a minute. So my screen got off. So yeah, back again. So whatever, again it got off. So there's some problem in the connection. Yeah, so all of you are able to hear me clearly and see, you are able to see the board.
Sir, the screen is not shared.
Screen is not shared. All right. So let me share the screen. Mm, Now you are able to see the board.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So I was just trying to describe what was happening here. So I can draw the circuit very quickly. I could have used the previously drawn one, whatever. So I will not draw the biasing circuit. So what we saw was we are putting some output cap over here. This is the output, final output, V out, and this is your V plus in, V minus in, and you are having some VB over here. And what we saw is that we are having to provide some significant delta V. So if this is 500 millivolt, you are providing something like 480 something, right? What was that? 475, right? What was the
Yes,
difference?
sir. Sir, one is
Something like
0.5 volt, other is 476 volt. Yes, sir. This much.
Yeah, so something like this. And now what is happening here is we are seeing that despite, here the DC current is also very skewed. So here what is happening is most of the current is flowing because in the first stage anyway, the VGS difference is significant here and here. And as a result, the I1, or you can call it M1, you can call it M2. So ID1 is significantly bigger than ID2. But and the current here and here are similar. That means if I call this, say, whatever, we call it M5, 6, M6, if I call it M6, so ID6, and if I call this M7, ID7, they are coming similar. But if you keep this same, like if it is 500 millivolt, then what is happening? Then if VDC plus equal to VDC minus. That means, or in a better term, I would say V in DC, input DC level. So V in plus DC equal to V in minus DC. That means the input DC levels are same, 0.5 volt. Then the ID1, ID2, the DC levels, they are same. But what is happening? ID6 is significantly less than ID7. This is the first case. That is what we have seen. What is the reason for that? So if your input DC levels are same, we are having the same current flowing in M1, M2. As a result, in M3, M4 also same current flows. And as a result, the VSG developed for M3, M4 will also be same. Whatever VSG you get for M3, same you get for M4. As a result, the VSG that you get for M7, same VSG you get for M6. So under this condition, the VSG of M7 and M6 are same. But the VSD of M7, VSD7 is significantly greater than VSD of 6 because 6 has, 3 transistors in stack in the load, whereas M7 has only this. So VSD of M7 is going to be higher. As a result, now in the output stage, ultimately, this current, if we call it say M9 or M10, whatever you call it right now, I'm not writing all the numbers, M9 or number 9, whatever. As a result, now if I have to equate this current, like for ID6 to be equal to ID9, what do I need? Because now the gate voltages of VSG 6 and 7 are same, but the current in M9 in order to be equal to M6, and especially the current in M3 is lesser because the current in M3 is same, but because of the lower channel modulation, M7 current is coming higher. As a result, the current in this transistor, maybe we can call it M8. So the ID8 transistor that is getting higher current, which is equal to the 7th current. Now 3 to 4 mirroring ratio is higher. Effectively, why it is coming higher? Because of the channel length modulation. 4 to 6 mirroring ratio, whatever you are getting. So ID6 by ID4 is coming less as compared to ID7 by ID3 for the input DC for equal input DC. What is the reason? That the VSD of M6 is lesser. VSD of M7 is bigger. Although the VGS are same, but VSD is bigger for M7. As a result, now if I keep the same DC voltage at the two inputs, and that is going to lead to a larger current in M7, M3, ID3, ID4 are same, but ID7 is bigger. Now, if ID7 is bigger, ID8 is also equal and bigger. So now ID8 is also significantly bigger. ID8 is going to be bigger than ID6. That means what is the situation? ID9 will try to sink more current than ID6. But that is not possible, right? Because ID6 and ID9 are in the same series. So in order to equate the current, in order to make sure that ID9 and ID6 are same, what is the option circuit has? The circuit will pull down the DC voltage so that the VSD of 9 reduces and VSD of 6 increases, right? So this will lead to lower V out so that VSD of 6 becomes significantly higher than VSD of 9. And as a result, the current becomes similar or becomes equal. So definitely in that case, the current in ID6 is still going to be lesser than the current in ID4. But now because we are, the output voltage is adjusted and is going down, we are making sure, the circuit is making sure that the current in ID6 and ID9 are same. Because ultimately in circuit it has to be same. ID9 and ID6 are same. Is this clear to everyone? So what is happening when we apply same DC to the both inputs?
Yes.
Yes, sir.
So once again, I will repeat, if your DC is same, means the input side, you are applying the same DC. ID1, ID2 are same. ID3, this also means that ID3 equal to ID4. This also means VSG3 is equal to VSG4. This also means VSG7 is equal to VSG6. But now the VSD, as I told you, VSD of 7 is, you can see, because VS6 is having 3 transistors below it, 7 is having only 1 transistor which is diode connected. So the VSD of 7, the so drain voltage of 7 is significantly bigger than VSD6. As a result, now this is going to get more current. So ID7 will be bigger than ID6. And as a result, ID8 will be bigger than ID6. And then ID9 is mirroring ID8. So ID9 will be almost similar to ID8. So now if I assume that ID9 is in saturation, the M9 is in saturation, just like M8. So the ID9 will be bigger than ID. So ID9 will be equal to ID8 and ID9 will be significantly bigger than ID6 because ID9 is equal to ID6, sorry, ID8, which is equal to ID7, which is equal to, which is greater than ID6 as we discussed. Why, right? So ID7 why it is bigger than ID6 because the VSD effect. This is the VSD effect, channel length modulation effect. Because the overall VSD available for M6 is much bigger, sorry, much lower as compared to VSD of M7. Now, if this is true, then M6 and M9 are in series, they must carry the same current. So the current in M6 and M9 must be same. It cannot be that ID9 is greater than ID6. That is not possible. So when this will be possible, when ID6 and ID9 are same, how will it be possible? Provided the DC level at the output goes down. If that goes down, then automatically the VSD of M6 will go up, VSD of M9 will go down, and it will balance the current. It will make the current equal. That's why initially when we apply same DC voltage, the DC voltage is coming too low, 200 millivolt or something like that, even lower than that. What was the value?
Sir, it was around 10 millivolts.
10 millivolts. So it was even lower, 10 millivolts. So that the VSD, the VSD of M9 is coming much lower. It is entering almost in triode, deep triode region, and current is reduced. So now, in order to, and this is going to be the low gain region because the M9 has entered into triode. And this will happen provided your lambda effect is very strong. Channel modulation effect is very strong on ID6. Right? So that means lambda value is big. 1 plus lambda ID that you write is going to be big. Then only this will happen. So what it looks like in this model, whatever they are using, lambda value is big. As a result, the channel modulation effect on the DC current is pretty big for M6 and M7. As a result, the current difference is coming. Now to solve this, what we did is that, okay, you reduce the DC value. So rather than 500 millivolt, you go down 475 millivolt. If you go to 475 millivolt, now what is happening in the modified scenario? For the modified scenario, I can write it down a little below. Maybe I can just copy paste the whole thing. Now, if this is a scenario where I have put M, gate voltage of ID, gate voltage of M2, I have put lower. Now, what is going to happen? For the first stage, definitely because the gate voltage of M2 is lower, I will get ID2, DC current in ID2 less than DC current in ID1. That also means that DC current in ID3 will be less than DC current in ID4. Is that clear? Now, if that is the case, now we know that ID4 is significantly coming bigger than ID3, significantly bigger. But the output point for V out to be equal to 0.5 volt, what do we need? See, if you look at the output branch, when will you get output close to VDD by 2? When the pull up and pull down strength, pull up and pull down paths are similar in strength. That means given saturation region condition, both of them are driving similar current, or basically capable of sinking similar current. So now, in order to equate the current and keep the device in saturation region, you have already trying to put the V out close to VDD by 2, and therefore all the devices will be in saturation. Now, for both the devices, all the devices to be in saturation and having same current, ID6 become equal to ID9. Earlier, what the circuit did, it pushed the lower transistor in triode region so that the ID6 becomes equal to ID9. Because ID6 was coming lower, it pushed the drain voltage of M9 low so that the ID6 becomes equal to ID9. But now we are forcing the output voltage and we are trying to set it to close to VDD by 2 so that all the transistors are in saturation. Now M9 is in saturation, M6 is in saturation. And we want equal current in both of them, which is, that means you need to have equal current in M9 and this M8, whatever you call it. So I need, of course, M8 and M9 current are same, and M8 and M7 current are also same, right? So up to, that means that I need ID6 and ID7 to be same. Then only this will happen, because ultimately ID7 is equal to ID9, because this thing is equal to ID9. Now, for ID6 and ID7 to be same, I already know that the VSD of M7 is big. So still, that is the condition, because the voltage headroom, that means the VSD that you have, VSD of 7 is still bigger than VSD of 6. Even if they are in saturation, it has to accommodate for, the VSG of this transistor also. So it has lower VSD. So the VSD available for 6 is anyway still low. So VSD of 7 is still greater than VSD of 8. Therefore, in order to make these two same, what do I need? I need VSG of 6 to be bigger than VSG of 7. That means VSG of 4 should be greater than VSG of 3. That means ID 3 should be less than ID 4. That means ID 2 should be less than ID 1. That means VGS of 1 should be less than VGS of 2. Is that clear?
Yes, sir.
Yes.
Yes, can you speak louder?
Yes, sir. Understood.
Yes, sir.
Yes, sir.
So now this is the reason, because the value of lambda is affecting the circuit, but I don't remember any such scenario in advanced technology node that we have used in Cadence, because probably the TSMC model that we are having, it doesn't have that kind of a larger lambda. So in this circuit, in this model, whatever lambda we are getting, we have to simulate according to it. So assume that okay, you have a bad technology with a large lambda value, because of which channel modulation is significant, and then you are having this kind of difference in the DC. But generally, I have not seen this kind of big difference required in case of TSMC models. TSMC is a foundry, right? All of you know TSMC? How many people have heard of TSMC?
Yes, sir. Taiwan Silicon Manufacturing Company.
Okay. So this predictive technology models are for academic purposes. TSMC, UMC, these are commercial foundries where the actual fabrication takes place. India has also got one foundry, SCL, where chips are fabricated. So these are standard foundries. Their models are standard models. I don't remember seeing this kind of anomaly in those models. So it all depends upon lambda value in this case. So now let us look at some more things. Where is my screen? So going forward, we can look at buffering of op-amps also. We can also look at feedback amplifiers. How do you make feedback amplifiers with this? So some people have already done the unity gain follower. So once you have a very high gain, you can do the unity gain follower example. So let us see. So in case of say unity gain, anyway, we are fixing the output voltage is equal to the input negative terminal, and then we are trying to sweep the positive terminal voltage and seeing the characteristics. So again, the input common mode range depends upon the output range as well as the input, the common mode range. So for the voltage follower analysis, the overall operational range will depend upon the ICMR, and it will depend upon the output range as well. If the output stage goes into, triode, then also it will fail. Input side also, if any of the devices are going into triode, then also it will fail. So it is going to be basically intersection of input common mode range and the output swing. If the output swing is limited, then that will be the bottleneck that will reduce the operation range of your common mode, of your voltage follower operation or unity gain feedback operation. Whichever is smaller, output range is smaller, then that will limit the voltage follower operation range. If your input common mode range is smaller, that will limit your voltage follower operation range. So that part has to be clear. And remember that what happens to the bandwidth in the closed loop? Closed loop, open loop bandwidth, if it is, A naught is the open loop gain. And bandwidth is a B naught is the open loop bandwidth. What is the closed loop bandwidth? Yes. What is the closed loop bandwidth? Yes, anybody?
Sir, A naught by 1 plus.
I have forgotten. You have not studied feedback. 1 plus A beta, you have not studied. Sorry. Beta is the feedback factor. All of you have studied this? And closed loop gain?
So A naught by 1 plus A naught beta.
Which is approximately equal to 1 upon beta. And why do we do this? Because then it becomes insensitive to A naught. Because beta is done by passive components, it is not dependent upon A naught. A naught is something which is dependent upon device parameters, which is highly variable. So from one amplifier to different amplifier, the gain value will vary very strongly. So this GM1, GM2, RO1, RO2, all these things are going to vary significantly from device to device. As a result, A naught is not a very reliable parameter. It may be very high, but it will vary. So by using feedback amplifier, we just use passive components in feedback, and their ratios are not so much device parameter dependent, and we get a well-defined, well-specified feedback gain or closed loop gain. Is that clear to everyone? So the bandwidth also, you get an enhancement. Whatever bandwidth you are getting in the open loop case, it will be 1 plus A naught A naught beta times the closed loop open loop bandwidth. So here, if you, for example, suppose for unity gain feedback, for unity gain, if you look at the numbers, your beta becomes 1, and A naught in this case is 10 to the power of, you are getting 300K. So even if I assume, say, 10 to the power of 5, right? So 10 to the power of 5, and your open loop bandwidth was how much? Suppose 100, 1 kilohertz, something like that. So what is the closed loop bandwidth? We are getting something like 10 to the power of 7 hertz, which is high, right? What was the 3 dB bandwidth? 1 kilohertz or 100 hertz? What was that?
So it was around 400 hertz.
400 hertz. And this was something like 3 into 10 to the power of
3 into 10 to the power 5.
So you can see you are getting 1.2 into 10 to the power of 8, right? So it's a pretty big. So exactly speaking, you are getting 1.2 to the power of 8 hertz. So almost 0.1812, gigahertz. So in terms of bandwidth, closed loop operation, you will still get good speed. And in terms of closed loop gain, of course, depending on the feedback factor, you can decide what is the gain. In terms of, say, any other feedback, say suppose you want to operate it as a negative feedback amplifier. So how will you bias it? How will you connect the feedback circuit? So negative feedback amplifier. Let me draw block level. So block level, if I see, ultimately you have studied this configuration, right? You can apply the V in over here. You can fix a VDC, and this is your R2, this is your R1. This is some DC voltage, goes to the VCM, whatever common mode voltage you are applying, and your output gain V out AC upon V in AC, small signal, that will be approximately equal to R2 upon R1. Exact number is, of course, divided by 1 plus A naught beta, and provided A naught beta is much greater than 1, you can get approximately equal to R2 by R1. So now the question is, how much big A naught should be? So again, A naught beta is again same thing. So now A naught beta, we are trying to get them much bigger than 1. How much bigger than 1 depends on the accuracy of the precision of the gain. So if you want very high precision gain and it should not be corrupted by A naught, then I need A naught to be much bigger than 1 by beta. So if I want 1% accuracy, so suppose I take 1 upon beta out. This is also on the top also we have 1 upon beta, and here I have basically 1 plus A naught beta. So if I take, say, beta out, and I am left with 1 plus A naught upon beta. Sorry, 1 upon beta plus A naught. And now I have overall gain, given by 1 upon beta times this particular factor. Now, if I want this factor to be, negligible as compared to A naught, because A naught has to be much greater than 1 upon beta. If I want this factor to be negligible and the accuracy should be more than 1%, what should be the value of A naught with respect to beta, minimum value? Sorry, I wrong. I got it wrongly. So let me just I mix two things. So this one will be this one will be A naught upon 1 plus A naught beta. Right. So A naught is your open loop, and I'm taking 1 upon beta. So you are left with A naught upon 1 upon beta plus A naught. So my target gain is this, and for that to happen, I need A naught to be much greater than 1 upon beta. How much greater? So that I'm saying, if this number, if I take A naught also out, suppose I take A naught also out, then this will be something like 1 upon beta, 1 upon 1 plus 1 upon A naught beta. And then I can write this 1 upon beta. This is 1 plus x, right? Where x is very small. I can write it 1 minus 1 upon A naught beta. Because 1 upon, assuming the factor, 1 minus 1 upon 1 plus x is approximately equal to 1 minus x for x much, much less than 1. This all of you know. So if this is the scenario, and now if I tell you that, okay, I want the gain to be more than 1% precise, what should be A naught beta value? Because any inaccuracy in A naught will lead to inaccuracy in the gain. My gain should be defined by only this factor and not by this factor. So if I want the gain accuracy to be higher than 1%, what should be A naught beta minimum?
Sir, 100.
100, right? Because if A naught beta is much bigger than 100, then I am sure that this factor that we are getting is going to be less than 0.01. As a result, the error will be always less than 0.01. So this A naught beta magnitude will depend upon what is the precision of gain that you are requiring. Suppose you are targeting a very high precision ADC. The ADC, your application tells you that DSP signal processing people tell you that my data precision should be very high. I need 10-bit ADC. 10-bit ADC means what? You are looking for 1000 levels, right? 10-bit ADC, the 1024 levels, almost approximately 1000, right? 1000 levels in the signal. That means the entire signal range that you're trying to capture, you are dividing it into 1000 segments. Therefore, what is that precision of the signal that you are looking at? 0.1%. So all the amplifier stages should not corrupt the signal more than 0.1%. Then only you will get, the resulting precision. Otherwise, if the signal is already distorted by beyond more than 0.1%, then keeping 10-bit for the ADC is not serving the purpose. In order to take the advantage of 10-bit ADC, you need to have the signal coming to the ADC after amplification 0.1% precise. That means none of the amplifier stages should add more than 0.1% error. Total errors, distortions, etc. added by all the stages should be within 0.1%. So for that condition, what will be the requirement? Requirement will be, for this case, A naught beta should be greater than 1000. Likewise, if you go for higher number of bits, higher will be the precision requirement. Suppose you want 16-bit ADC, further, higher A naught beta requirement. In this case, anyway, so if your gain is suppose 10 to the power of 5. So here, the thing is that for a given gain, for a given closed overall closed loop gain, what is the A naught beta we can have. So here, first thing is that we are getting a requirement for the product A naught beta. So if your beta in this case is high, that was 10 to the power of 5. And then you have, this thing. So what is the beta value you can have? So beta will be in this case 10 to the power of minus 2. That means 1 upon beta can be 100. That means in a single stage, you can aim for a closed loop gain of 100. You should not have more than 100 gain in one stage. If you go beyond that, then you will need a higher A naught also, right? Because the gain is 1 upon beta. Are you getting the point? So this constraint is telling us that how much closed loop gain 1 upon beta you can have from a single stage, provided the A naught is 10 to the power of 5. So this means that overall, if you're trying to record a signal, which is say 1 millivolt, and you want to amplify it to full range, the ADC sitting over here, ADC, its input range is 0 to 1 volt. It can handle 0 to 1 volt, and it will produce a 10-bit output. Now this range 1 volt, there has to be an amplifier, filter, whatever filter you ordered right now. Suppose you don't have filter, you need an amplifier A, which will convert this 1 millivolt into peak to peak 1 volt, right? Because ultimately I have to take the entire ADC range into account. I have to utilize the entire ADC range. If I don't utilize it, what will happen? Suppose my gain is lesser and I am utilizing only, I'm only amplifying by 100. So it is only suppose 0.1 volt. What is the problem? Still the ADC can work. What is the problem? Is there any problem? Yes, anybody?
Sir, the ADC has 10 bits, right? So it has a resolution of 1024. So this the signal which the ADC receives, it will split basically into 100 and 1024 parts. So now if I have magnified only up to 0.1 volt, the data which there may be loss of data. While if I amplify it to 1 volt, the chances of loss of data is less.
What do you mean by loss of data?
So like
There is no loss of data. So
Sir, will
only
the
thing is
SNR be improved?
the ADC is giving you the characteristics of the ADCs. If I am plotting V in across the input starting from 0 to 1 volt, the output code is for 1 volt, it will go to maximum value, whatever it is. So if it's 10 bit, it will go to 1 1 1 1 1 1 1 1 1. Starting from 0 0 0 0 0 0 0 0, midway it will be 1 0 0 0 0 0 0 0 10. So if you look at the ADC characteristic, it will be like a staircase function, tiny staircase, linearly increasing, something like this, going all the way to maximum. It will be exactly, straight line. The way I have drawn is a little dirty, but it will be straight line, staircase kind of function. It will be going all the way to, this 1 1 1 1 1 for input voltage equal to 1. But now your input signal is within 0 to 0.1 only. So you are actually utilizing only 10% of this range. Maximum value is only going to be 10% of the maximum. Right? That means you're not utilizing majority of your ADC range. You're utilizing only small fraction of your ADC range. Your output, effectively, your output number of levels are going to be 1/10 of the actual levels available. So you are not getting effectively 1,000 levels in the signal. The recorded signal, you will have only 100 levels because you are utilizing only small fraction of the input ADC range. Is that clear?
yes, sir.
So even though the ADC is capable of doing the job of 10-bit digitization, but you are utilizing, if you're not amplifying the input signal to the input range of ADC, you are utilizing only a small fraction of the input dynamic range of the ADC. That means you are also utilizing a small output range of the ADC. That means effectively your signal resolution is going to be 1/10 of the ADC resolution. So 10, that means number of levels will be 1/10. That means if you're having 1,000 levels in the ADC output, you're utilizing only 100 levels. That means around 7 bit. Rather than 10 bit, around you are getting around 7 bit, because 7 means 10 to the power 2 to the power of 7 means around 128. So you are getting around 7 bit ADC or 7 bit data effectively. So your resulting digitized data, it will effectively have a resolution of 7 bit only, not 10 bit. Is that clear? That's why it is important that we amplify the signal to match the ADC range, whatever is the ADC range. Now, if that is a scenario, now net gain required in this case is 1,000. But I can't say that you take this open loop amplifier and put R1 by R2 equal to 1,000, and then you will get the gain. That is not good, because here it is giving a constraint that 1 upon beta should be less than 100. That means your overall closed loop gain for a single stage should be less than 100. So then what I can do, I can have 2 stages, and then overall gain of these 2 stages, A1, A2, I can divide, so that A1, A2 total is coming around 1,000. So maybe around 33, something like that. So that this constraint is also satisfied. Beta 1 upon beta is less than 100. And at the same time, overall gain, whatever is the overall gain, you're getting it. Is that clear?
Yes.
Yes, sir.
So that's what we have to keep in mind. So for designing a signal chain, when you are doing any signal acquisition and trying to amplify it further, depending upon the application and the ADC interface, we will need this kind of. Now, going forward, let me now copy the circuit. Drawn too many arrows. So feedback point of view now, if I look at the feedback connection, the actual feedback connection using resistor that we are planning to do. So this size can also be reduced, I guess. Yes. Yeah. Let me clean this a little bit. I should keep one diagram drawn which is clean, so that I can keep using it, because otherwise every time I either have to clean or I have to redraw, which is not good. So I will remove unnecessary thing for the time being. So this I will copy and keep, so that I don't need to keep drawing. Right. This. All right. So let me just maintain a copy somewhere. Let me come back to it. I will keep it as a buffer. So now. Now, when you're talking about, say, the feedback connection, so how are we going to do the feedback connection? So let me draw it using R, the another color. So my negative amplifier, inverting amplifier, for that, let me blue and draw the resistors. How will it look like? So output side, I have to connect to the input. So I need to have a connection from here to the input. So I can maybe take it from here and bring it here. And I need to apply the input here. This is my R2. This is my R1. And the input can be applied here, V in. So this is one way. So in this case, of course, whatever DC you apply, so whatever DC, VDC, or V common mode, whatever. So whatever DC voltage you apply, that same DC will appear here. So suppose you are applying 0.4, 0.5 volt. So the circuit, the negative feedback will make sure that it is 0.5 volt. And then you can apply some input over here that will result in some output swing over here. So in this case, when you are applying resistive feedback, how will we decide what is the signal swing available at the output, and also what is the input range here? So suppose in this case, the gain that you are assuming R2 by R1 may be big. Suppose R2 by R1 is, say, 20, or suppose 100. So R2 by R1 100. So in this case, when your input signal is changing here, so at this node also your signal gain or the signal amplitude will be less, but at this node your signal swing is going to be much bigger, right? So as compared to 0.5 volt, it will go much higher and lower. So this point you're going to get much bigger swing. And here the input side, the signal is much less because it is 100 times less. So I can ignore it. So in terms of AC ground, this is an AC ground, this is an AC ground, and whatever Vin you are applying Vin upon R1, the small signal I in that you are getting is approximately Vin upon R1, small signal Vin upon R in R1. So don't confuse DC with AC. So if you're applying an AC signal Vin, of course it will have some DC bias as well. At this point, you will need some DC bias. You can't apply 0. So the DC bias, suppose, is also same, whatever 0.5 volt. So the input will have to have a DC bias which is matched with the DC bias of the input device. If you have a significant DC difference between this point and this point, that means the DC current itself here will be pretty big, and that DC current has to ultimately flow in this direction, and it will sink from the device. So that is not good. So if you have a difference between the DC of this particular stage and the previous stage, even a small difference, that will lead to a significant amount of current flow between these stages from R1 to R2, and that additional current will be provided. Suppose suppose this signal is lesser. So suppose this is small by 0.45, 50 millivolt. If it is 0.45, then R1 upon 0.45, R1 0.05 upon R1 current will be flowing this way, and that has to be supplied from this device. Therefore, now this upper devices will be catering to more current. It will be taking some current from the upper devices and diverting it to the DC. That will have more complication for the DC bias. The DC bias of the output stage will not be as per expectation because some of the output stage current is flowing into the input. So in this case, it is good to have a well-matched DC so that the DC conditions here and here are perfectly equal. They are well matched. But again, because of variations in the circuit, etc., it may not be always possible because you have seen that small variations in the circuit may lead to a difference between these two values. You may have a significantly different value over here. So right now what we got is an extreme, but at least few millivolt difference you will get because of finite gain, because your gain is A0 upon 1 plus A0 beta, and it is only approximately equal to 1 upon beta. But the exact value is this. So,
sir, can you explain this part once? That how is this DC point of M2 becoming same as that of M1?
Negative feedback, what happens, right? So in your negative feedback, if you have a very high gain amplifier, so all throughout you have been studying that in a negative feedback, voltage follower, how does the voltage follower work? Ultimately, if you have an ideal op amp, we say that these 2 points will always be same. Whatever VDC you apply, it will appear here VDC. Why does it appear? Because of the negative feedback. So, why, why I would say the concept of, I would say, virtual ground. Why virtual ground? So virtual ground is the concept we have been always using. So that part we can explain again. Maybe let me just bring that copy again here. So if you are putting a negative feedback means suppose you are putting a voltage feedback configuration here, you are bringing it back, negative input, you're connected. And now you are applying a DC over here, VDC. So what we assume is that this voltage will automatically be following this voltage, provided the gain is high. Whatever change you make here, the same change should appear here. So DC point of view, they will be matched. This node will be exactly tracking this node. Why this should happen? So now, if we assume that you increase this by delta V, so what should happen to the output?
The output will be amplified A times delta V.
Yeah, so again, output will increase. Till what point will it increase? Till there is a net small signal current, right? So any difference between the two levels, VG1 and VG2, will produce a net delta I, right? The net delta I will come here. So that net delta I will flow is proportional to what? It is ultimately dependent upon whatever the gain, the small signal gain you are having, transconductance gain times delta V. I would call it transconductance. So ATG times delta V. So as long as there's a difference between the delta V, there is a non-zero small signal current flowing at the output. So as long as suppose initially both were same and now you increase this DC voltage by delta V, that will lead to a non-zero positive delta I here. From here to here, the gain is positive. So it will lead to a delta I that will lead to increase in this voltage. Till what point it will increase? Till this becomes again equal, right? So if this was VDC plus delta V, this also goes to VDC plus delta V. Then only the net again small signal gets cancelled, because now when this becomes auto delta V, then the two currents will be balanced and there will be no difference between the up and down current. Then it will stabilize again. Is that clear?
Yes, sir.
So just looking at the gain and the small signal current flow, we can understand that the moment you create a difference delta V between the two DC levels, when the two voltages were same, initially when the two input voltages were same, this current and this current, this current and this current, this current and this current, and as a result, the M6 current and M9 current were same. There was no difference between the M6 and M9 current. But now the moment you create a difference, suppose you give a step jump delta V at 1, now that has created an imbalance. Now this has increased the current here, this is going to increase the current here. But now this increasing current will lead to what? It will, now the M9 current, assuming that it is remaining similar, but eventually this delta I, which has increased in M6, why it has increased? Because M1 current has increased, this current has increased, as a result, M6 current has increased. Now it will keep on increasing the output till the point where your output voltage, the M2 gate voltage also goes up, so that now these two current again become balanced. Otherwise, what will happen? Initially, when we saw that the upper and downward current were same, that these are same because of mirroring from the previous stages. Now, when there is a mismatch in the first stage itself because of delta V being created, that is leading to an increased current in M6 when you are increasing the M1 gate voltage. Till what point it will remain higher? Till again the output voltage here, this output voltage goes up and becomes equal to the VG1 plus. That is the negative feedback concept, that it tries to follow the signal applied at the positive terminal. So the same thing, whatever feedback amplifier you use, in whatever application you use, you may have many more stages than this, but ultimately this will be the concept. Is this clear?
Yes, sir.
You can try to do an analysis, you apply the step. Initially, you keep them same, whatever DC value you are getting, for example, and then you apply a step jump, and then you will see that how the transient current flow in different branches and how they finally become zero and settled again. So now going back. So what was I talking about? So I was talking about the DC current flow. So in this case, when you're having resistive feedback, one of the concern is that the DC voltages at the input stage must be matching with the common mode voltage of the amplifier. That means the DC here and here should be same. If it is not same, what will happen? There is a non-zero DC current flowing through R1 and R2. And if there is a non-zero DC current flowing through R1 and R2, remember that R2 is much greater than R1. So there will be a big DC difference between M2 gate and the output, which is not desired, right? So we want this to be equal. When will it be equal? When your DC current in R2 is negligible. But here, if you create a difference between DC here and DC of the gate, then definitely you are going to have a DC current in R2, which will lead to a difference between the output voltage and this. And along with that, that DC current has to be supplied from the output stage. And then you will not, the mirroring will be disturbed, and you will not have the same current coming from the pull up and the pull down. All those things will come into picture. So the resistive feedback scenario, we need to make sure that every stage, the common mode DC level is similar. That can be challenging, especially given the variations, etc. Whatever DC voltage you apply, it may not be same at every stage. So you may have small differences, and that may lead to problems. That may lead to saturation of amplifier. Even a small difference in the DC level here and here, it may create saturation in the amplifier. Saturation means if there is a small difference in the DC level here, and that is leading to a DC current flow, that may lead to the output going completely high or completely down, depending upon the direction of current flow. So for example, in this case, when I say that input difference, the input side, the DC is slightly lower, 0.045, slightly lower, and the current is flowing in this direction initially. That means that from here to here, the current is in this direction, and from the gate to the output, this direction, the current will flow from output to the gate of M2. As a result, this voltage will be higher. This will push the output node towards very high value. It will become close to VDD. It will completely saturate the amplifier, not even work. So therefore, this matching of DC level from stage to stage, we have multiple stages of amplifiers, A1, A2, just like we discussed in the last example, right? A1, A2 being equal to thousands. This will make this has, if you have to use this amplifier, you have to make sure that the DC levels here and here and here are exactly same, very well matched, not even a millivolt of difference. That becomes challenging. That's why people avoid using this resistive feedback, especially in your multi-stage scenario. So what is the solution to this? You are getting the problem. I hope if you simulate this, you will get an idea that in the moment you create a DC difference here, small difference, even few millivolt of difference, you will see that there's a DC current, and the DC current flowing through R2. What will it do? It will create a difference, right? As compared to voltage here, it will create a much bigger difference. Output can be pushed to very high or very low value. Is that clear to everyone?
Yes, sir.
Yes.
So now so this is the problem with resistive feedback. So to solve this, people generally go for capacitive feedback, where you have the AC and DC decoupled. You don't have to worry about the DC level. So then we have capacitive feedback. So again, I can copy that amplifier. So capacitive feedback, what will happen? You use a C1 over here. C1, C2. And here apply the AC signal. Whatever with the DC, now the DC is not material. Whatever is the V in AC, DC is decoupled. So whatever AC signal you apply, that will get amplified and appear here. And the equivalent op-amp block diagram will be something like this. What is the gain? What is the gain of this?
C1 by C2. C1 by C2.
C1 by C2, right? So Z1, this is Z2 by Z1. The gain is Z2 by Z1 minus Z2 by Z1. So minus C1 by C2, because Z2 is 1 upon omega C1, Z C2, and Z1 is 1 upon omega C1. So gain is minus C1 by C2. So there is no DC current flow. There is no problem with the DC biasing. So each stage can be biased independently. You don't have to worry about exactly matching the input and output DC of every stage. So this will simplify the design. It will make it more tolerant towards variations and variation in the DC bias, etc. And the problem now is, what is the problem in this circuit? You are applying the DC level over here, VCM. Any problem?
Sir, at high values of frequency, these may get shorted, right? Because the impedance will be lower.
Okay, so high value anyway, high frequency, you get 0 dB gain. So that will happen eventually. So that's not a problem. Anything else? Yes, any response to this? You don't see any problem in the circuit?
Sir,
Yes.
sir, when we were learning op-amps, we were taught that the output resistance of an op-amp is nearly zero or negligible. But in
So
this output configuration, the output resistance isn't negligible, right, sir?
So that's why we need a buffering stage to make it 0. So this is generally the difference between OTA, operational transfer conductance amplifier, and op-amp. So right now we have not yet reached the op-amp. We are still at the OTA stage, operational trans conductance amplifier, because output impedance is high. So output impedance of which kind of amplifier is high? Trans conductance amplifier. So right now it is still a trans conductance amplifier theoretically. But if you want to make it close to an ideal operation amplifier, you need to add a buffering stage that I will cover next. But
Thank you, sir.
in many applications, without buffers also it can be used. Why it can be used? Because in the closed loop, what is R out? What is R out?
R06. Oh, it is like
R out open loop divided by 1 plus A beta. Have you studied this? A naught beta.
Yes, sir.
So the closed loop output impedance becomes open loop output impedance divided by 1 upon A naught beta. If your A naught beta is big, then R out becomes smaller. So for example, in this case, the R out without buffering, the R out is GMRO whole square. So GMRO whole square means 100 times, again, maybe 50, 60 kilo ohm. So 100 times GM RO may be 100 and GM RO times RO. RO may be suppose 10K or 50K, 10K, maybe slightly higher. And A naught beta, I am saying that, okay, in this case, suppose beta is, A naught beta is suppose 1000. So still, I'm getting around just 1K. Right? So output impedance, even if it is a voltage follower, output impedance is still less. Closed loop output impedance is still less. So if I'm using it as a voltage follower, the analog signal, here is analog signal. So here the output impedance looking into the voltage follower A equal to 1. Here output impedance is still comparatively low, only around 1000 ohm. But if you want to make it further lower, there are, you need to add a common drain kind of buffer so that the output impedance in the open loop itself is low, which is around maybe just a kilo ohm or something, few kilo ohms or less than that. Then the output impedance can come down all the way to few ohms or few tens of ohms. So in case when we need that kind of output impedance, then we need to buffer it. So in many applications, the output impedance has to be even lower, further lower. So it depends upon application. In many applications, without buffering also you can use it. It will be called unbuffered op-amp. This is an unbuffered op-amp. Okay? But when you add buffer, then it becomes closer to an ideal op-amp, and then you have a buffered op-amp. But everywhere it will not be required. Yes. Any other question? Okay. So going ahead, what was I talking about? The problem in the circuit. So nobody has shared any problem in the circuit. You try to, that whatever you said is not the actual problem. That is a different thing. In this circuit, is there any other problem? Biasing side or anything missing? I already gave you the answer, half.
So the common mode input which will be provided.
Sorry?
So we can't provide the common mode input for the V in before the capacitor because the DC will be blocked.
Can you speak louder? Somehow your volume is not very good. Hello? Yes, am I audible?
Yes, sir. Sir, for the MOSFET number 2, the for its biasing at the gate, the common mode voltage needs to be applied. But we can't add it before the capacitor because it will be blocked by the DC.
Yes, so the capacitor will block the DC, so there is no way to have a DC current. So the DC point of view, this DC voltage V out DC will not reach the gate of M2. So M2 is a floating node. Actually, the DC point of view is disconnected. It has no connection to any DC level. Earlier, it was at least shorted through the R. So the R will provide DC path. So it will ensure the DC, is established and it is equal to the output DC. But in this case, there is no DC. So how do we establish the DC? How do we establish the DC here? Can I put a VCM here?
So we can use some resistor in parallel with the capacitor.
Okay. You have seen my lectures recorded?
Yes, sir.
Okay. Then you have the answer. But what about this? Quickly, what about this? Is it going to work? Tell me quickly, this thing should come very quickly.
No, sir.
Why will it work? Why will it not work?
Sir, because like we will be imposing two different voltages at the same node.
What do you mean different voltage? Where is the different voltage?
So like if we connect the source like VCM directly to that node, then we are forcing the voltage to be always at VCM.
Yes, so there is no small signal AC, right? It becomes an AC ground. If you put a DC voltage here, it becomes an AC ground, so there is no AC signal going to flow. So that is not possible. So we can't just short it like this. We can't put that DC voltage here. So the way we will do it is that you put a large resistor between the output and this point. Very large resistor RF. Why very large? Because what we want is a DC point of view, it should just become equal. But AC signal, it should not pass. Means AC signal point of view, it should filter it or it should block it. RF should not decide any AC gain. So if RF is very large, what will happen? You can treat it from the point of view of AC, you can treat it almost like a open circuit. Why? Because again, ultimately, if you find out the transfer function, it is a combination of ZF, right? So whatever the feedback impedance, Z feedback, what is it? It is RF parallel 1 upon omega C2. If it has to become independent of RF and just dependent upon C1, C2 ratio, then it has to be the impedance has to be mostly divided by 1 upon omega C2. RF has to be much bigger. If RF is close to infinity, then definitely this will automatically become 1 upon omega C2. Then your Z1 by Z2 ratio will be defined by only C1 by C2. RF will not play any role. Is that clear? So we want RF to be very high. And another reason is that RF, if you look at it, it will be again forming a high pass filter with C1. So C1 and RF combination, if you take the Z1 upon Z2, suppose you, for the time being, just take a superposition. You have C1, C2, and you have the RF. So RF side, or if you just derive the combined transfer function of this, RF, C2 and C1, considering Z2 upon Z1, RF will lead to a high pass function. And that as a result will block lower signals. That means lower frequency signals. That is not desirable. We want to, have larger and larger RF so that the high pass pole is shifted towards very low frequency. If your RF is not very high, then that high pass pole will be towards higher frequency and it will basically block your lower frequency signals. You will get something like this. If your RF is bigger and bigger, you will get, this will come closer to origin. So we want this, that RF should be much bigger so that the gain is independent of RF. And second, the C2 by, the high pass pole over here is closer to the origin. In some applications where we intentionally want to filter out signals here, maybe we are only interested in some signal in this range, then we can choose RF accordingly so that it can filter out signals in certain range, lower values. Upper range, anyway, you will get some 3 dB cutoff because of the high frequency behavior, but lower range, RF can filter out some signals. So there will be a omega high pass and there is omega 3 dB for the low pass. So omega high pass will be decided by RF, the RF value. Higher is the RF value, the lower will be your the omega high pass. Hello, am I still audible?
Yes, sir.
You think the power has gone or something? My inverter has turned off and I need to do something. And as a result, my screen has also turned off. The writing board that I'm using, that has gone. Well, I hope it will work. I've turned it off and on again. Let me see. So now the thing is RF, for the time being, maybe you can just simulate with very large RF. That large RF may be as high as 10 to the power of 12 ohm, something like 10 to the power of 12 ohm. So ideally, we would like to have a very large RF, but in this case, what I'm saying is you can just simulate with a nominal RF, very high RF of 10 to the power of 12, and then try to see what kind of closed loop gain you are getting, and also the cutoff frequencies, like the lower side, what kind of cutoff you are getting, higher side, what kind of cutoff you are getting. The both frequencies you can check. You can also analyze that if you use only resistive feedback, what happens because of the DC mismatch, if you have small DC mismatch, what is the effect on the output? Both these analysis you can do. So any question before we conclude? I will tell you, I'll give you a lecture link where how to make that RF using transistors that is described. Very simple. I can describe it shortly also, but I'll give you that lecture. Any question
Sir,
before we
it is
conclude?
that so it is the pseudo resistor concept, right, which you discussed in your lecture, NPTEL one.
Yes, 2-3 transistors will be there, something like this. But again, it will take some more time to describe rather than that, things which are already recorded, why to repeat? You can just, you can have something like, sorry. So this goes something like this and wait a minute. So you can use say PMOS, and what we do is we have the gate transistors, something like this will be connected to, there will be a circuit like this. I forgot the connection. Let me remember. So this one
Sir, it was
was,
between I think gate of one and source of the other, and then between the gate of the second and source of the other.
yes, it's something like this and something
Yes, sir,
like
it was
this.
like this. So,
And then you have this positive terminal, negative terminal. So what happens in this case is that you have uh, this is again given in some papers. There are some other ways of improving this also, but this is one of the common ways in which high impedance resistance can be optimized, can be designed. So here the length must be big. So the W by L is such that the L is quite big. You may have to choose one micrometer or something like that. Even if you're using scale technology, the length should be big so that the overall on resistance is big. And the thing is that on one side, suppose you're having virtual ground because the resistor on one side is connected to virtual ground. So suppose this is fixed DC, VDC. Suppose it is this particular node, and other side you are getting signal because it's a gain amplified signal. So here this side you will get signal, other side it will be DC. So despite the signal coming on the other side, you are always going to get one of these transistors in cutoff because suppose uh, the DC at the output and the input is same. So this DC level VDC because it's connected between the output and the input negative terminal, and both the DCs are same. But now when the signal is going up at the output, what is going to happen to the virtual ground is that is remaining same, but what is happening to the transistor M1 and M2? So this is the gate of M1 and M2. Now, when the signal is going up, then this signal, the gate voltage is higher. As a result, this is going to be turned off strongly, right? Because this is a DC voltage and this signal is gate voltage is higher than DC. This signal is also going to be anyway higher than DC because this is on the other side. So as a result, the VSG of the M1 is going to be strongly negative and it is going to be off because the gate signal is higher. Other side, if you look at this, the gate signal of the M2 right now in the positive cycle, the gate signal of M2 is low, it is VDC. Source signal, if I assume that the higher terminal, this is the higher potential terminal at that point. This is higher, but this is going to be turning on fine, but the other MOSFET M1 is turned off. Because of that, the series resistance is still high. And same thing will happen in negative cycle. Negative cycle, this one will be turning on, but this one will turn off. Because in the negative cycle, this signal is going down and gate signal is up. This signal for M2, this is fixed at VDC in the cycle, but this negative cycle, this signal is going down, source signal is going down. Therefore, for the M2 is going to be turned off strongly. M1 is going to be on because M1 side, the signal has gone down. So this is your, the signal at M1 is going down, but M2 is off. So from on at both cycles, these resistance are remaining turned off. And as a result, you get high impedance all throughout. When the signal is close to VDC, anyway, both of them we get VSG significantly less than VT, close to zero. So you get maximum, the on conductance will come here because both of them are getting almost like, uh, you're going to get a significant, equal, your VSG will be same. Both of them will be in subthreshold region or close to, cutoff. And extreme values, one of them will be on, one of them will be off. So overall, you can still obtain a very high resistance all throughout. And if your channel lengths are bigger, it contributes to higher resistance. So using this thing in series, you can basically design a very high resistance value effectively. In silicon, if you look for resistance value, maximum values you can have using different resistors is say a few mega ohms. So there are different, there are metal resistors called Rn, there are metal resistors which are made using metal segments. These are lowest resistivity. So metal resistors are just like small metal segments, very low resistance. So in case you need very low resistances, people use metal resistors. There are doped poly resistance, doped poly resistances are, as the name suggests, the poly, whatever poly is used for manufacturing the gate, the same poly is used to manufacture the resistors also, because it is having high resistivity. So if you dope the poly, it will be having moderate value of resistance. So this will be few ohms to few hundred ohms. This will be few kilo ohms. to a few tens of kilo ohms. And then there is undoped poly. Undoped poly will have high resistance, several hundred kilo ohms, 2 mega ohms. Now, if you can keep connecting things in series, the undoped poly, if you make a big segment and connect many large segments in series, then it will become several hundreds of mega ohms, but that will be very big in area. So here we need much bigger, giga ohms kind of resistance. So in that case, none of these can be used effectively. That's why we are using this technique. And why do we need giga ohm? It will become clear that when you simulate and when you first you simulate with the ideal resistor, and then you find out the cutoff frequency, and you see that for what RF you are getting cutoff frequencies of say 1 hertz or something, so that your signals are not suppressed. So at least if not 1 hertz, you try 10 hertz. So for 10 hertz WHP, omega HP, what is the RF value you need? You can first you can estimate using simulation, and then use of idea value first, and then check with this particular configuration. There are some other techniques also reported in literature how to implement very high value resistors. There may be some variations of this. There are different topologies. This is one of them. So first experiment with the ideal value, and then look at this particular scheme. Any question? So I've already described the assignment to you. So those who are present, they can carry out the 3 steps. First thing is connecting the resistive feedback, and then trying to see the effect of the mismatch in the DC between VCM and the input DC, and see how the output value is affected. And second, then using the ideal resistor RF and using capacitive feedback, then applying the AC signal, getting the gain. And third, you can vary the RF and try to see how the cutoff frequency is changing, and then try to implement that RF using this. Now, again, in this technology, the kind of model we are using, I'm not sure whether you will get correct behavior for this, because the lambda models are not very correct. So it is possible that in this PTM model, even if you design this thing, you will not get very large R. So that is possible. So we have to see, we can try and see what is happening. But in actual technologies, in TSMC, etc., we get decent resistances with this kind of structure. So you can try and we can see what happens. If it works, well and good. Any question before we conclude?
Sir, for this next assignment, can we use the 180 nanometer technology? Because in the 45 nanometer technology, sir, as I showed you, there are many like DC skewings are taking place because of the channel and modulation and all. So, sir, none of these will work properly. This capacitive feedback and all.
Capacitive feedback will not have any problem. Only this resistor will have problem.
Yes, sir. That resistor will also face problems.
If you use ideal resistor, it should work. If you use this resistor, it will have problem. So you can at least simulate using ideal resistor. Otherwise, you have to design the whole op-amp in in this technology. So first you use the ideal resistor and see what is the value coming. And you can try to simulate with this one, try to increase it for the cross-coupled transistor, try to increase the channel length, try to see what value you are able to get. And then based on that, you can estimate. So one way to either you can directly put it in the circuit, or you can estimate the small signal resistance by putting the DC value over here, put a DC value, VDC, put a DC value over here, plus AC value over here, VAC, whatever. So and then measure the AC current. That way you can estimate what is the small signal impedance going from one terminal to another terminal. So that is one way. Otherwise, you can also put it in series with the capacitor and try to see what is the cutoff frequency coming. So both ways you can use to estimate what is the resistance you are getting. Larger channel length will help, as I told you. So you can go to even 5 micro, 10 micro channel length. So you can try it. But only thing is the model may not be very accurate. So you have to see how correct behavior you are able to capture. But other things, at least the op-amp behavior is okay. You are getting good gain. You can try to reduce the gain a little bit. Right now you are getting 300K. That is not required. You can go to maybe at max we need maybe 50K kind of gain. So 50K is also okay. Any question before we conclude? Yes, any question before we conclude? I will stop recording. Any question? Last chance. Any question before we conclude? So tomorrow, by tomorrow, this analysis or feedback amplifier, etc., you have to complete. Any question?
Can you repeat the problem with